Day class. This is the recording for the remainder of topic 2 for week 2. So it's slides 42 through to the end of the slides. Now, up to this point, I've sort of hinted at what we do when we've got compounding of interest at something other than annually, or we've got payments that aren't annual, etc. But let's go into that in a lot more detail now today. So we're going to look at instances or what we do when interest is compounded more frequently than annually. We're also going to take a little look at how we amortize loans, and yeah, we've got a retirement example thrown in there as well. So let me share my screen for our slides, and I need to start my slideshow. On the current slide. Good. Okay, so interest compounded more frequently than annually. This happens often. So when you quoted a rate by a bank, it's always going to be an annual rate, but you have to find out how many times a year they're going to compound interest. Similarly, if you offered an investment rate, you need to ask the same question, because it might turn out that you're in fact paying or earning something very different from that quoted rate, depending on the frequency of how often interest is compounding. Because some institutions compound interest semi-annually, in other words, twice a year, every 6 months, others quarterly, every 3 months or 4 times a year, monthly, or even weekly, daily, or even continuously. We don't have to worry too much about continuously, but I'm going to show you how you deal with such instances. Let's demonstrate. Okay, Spool invests 1,000 Rand for 1 year. Now, if the interest rate was 10% compounded annually, okay, and you assume that if nothing is said about compounding something other than annually, he would earn by the end of year 1, 1,000, his original PV investment, times 1 plus the 10%, he'd have earned 1,100 Rand. If, however, the interest rate was going to be compounded twice a year, so it's 10%, but it's compounded semi-annually, then what happens is after 6 months, his 1,000 Rand invested will grow by half of 10%, which is 1,050. And then that is reinvested. And for the second half of the year, it earns another 5%. Okay. And then he ends up at the end of the year with 1,125. So can you see that he's earned extra, 25 Rand extra, in fact? Why can't I see my, there we go. When interest was compounded annually, he would have ended up with 1,100 Rand at the end of the year. When it's compounded twice a year, he ends up with 1,125, which is 25 Rand more. So he actually earned an extra 25 Rand because of the interest on the interest that he earned in the second half of the year, because the bank compounded it twice a year. Now, as far as our formulae or our financial calculator inputs are concerned, we've got to adjust everything to the frequency of compounding and also in accordance with the payment frequency. I've spoken about that golden rule before when we're considering an annuity or a perpetuity. So more generally then, our formula of FV is equal to PV times 1 plus R to the power of N becomes, when we're compounding more than annually, FV is equal to PV times 1 plus your nominal annual rate, okay, that's quoted, divided by M, and M is the number of times interest is going to be compounded in a year, And then that is raised to the power of that same m times your n. Okay. So m is the number of times interest is compounded per annum. Rn is the annual percentage. It's the R that we've been using up to this point. Okay, but we're just now going to give it a more appropriate name, which is your or indication that it's your nominal rate. And sometimes it's called an APR, an annual percentage rate. Sometimes it's called a nominal rate. And it's your quoted rate the bank gives you by law. Now, the true rate that you earn or paid, given the fact that interest is going to be compounded something other than annually, is called your effective, your annual effective rate. Sometimes it's called an equivalent annual rate, an EAR. It's your annual effective rate, and we'll call that RE. That is equal to 1 plus, in brackets, your nominal rate divided by m to the power of m minus 1. So that's just solving, it's rearranging this and solving for your actual interest that you're going to be earning. So in the previous example where the quoted rate was 10% and it was compounded semi-annually, and after a year, Spoo ended up with 1125 rands, what he actually earned in that year was not 10%. It was 10.25%, which we work out by using the formula 1 plus our effective rate, our nominal rate of 0.1 divided by 2, because that's the number of times interest is going to be compounded in the year, to the power of 2 minus 1. Okay, so when interest is compounded annually, there will be no difference between your nominal rate and your effective annual rates. Okay, it's only when interest is compounded something other than annually that your effective rate that you end up paying or earning on a loan or investment, whatever the case may be, it ends up being a lot more than your nominal rate because of the effects of compounding, which I illustrated on the previous slide. The 10% in that example is, as I said, the quoted or the nominal rate. It'll be nom percent on your financial calculators. It's RN in the formula. And you find that by multiplying the periodic rate. So, for example, a monthly rate or a weekly rate or a daily rate by the number of periods in 1 year. So the daily rate times 365, a monthly rate times 12, etc. This nominal rate is the annual rate that has to be disclosed to consumers by the bank. So that's what you'll be quoted, an annual percentage rate or a nominal rate. Your annual effective rate, on the other hand, EFF percent in your calculator, or RE in the previous formulae, which was 10.25% in our example, that's the annual rate of interest that you'll actually be paid, actually have to pay or earn, depending on whether you're borrowing or investing, after accounting for the effects of compounding during the year. And if you want to compare two alternative investments or loans with different compounding periods, you can't just compare them on the basis of their nominal quoted rates. You need to compute their effective rates and use that for your comparison. Okay. Now, the 5% in the previous example, which we got by dividing 10 by 2 because interest was going to be compounded twice a year, that 5% is your periodic interest rate. So it was a 6-monthly rate in that example. And it's your quoted rate divided by the number of periods. Your nominal rate divided by the number of periods. Never divide your effective rate by the number of periods per year. That will not give you the periodic rate, and you can't use it. Okay. It's something very different. Now, when we use our calculator, we've got a very easy method of converting a quoted or nominal rate to an effective rate and vice versa. firstly, you should check your PYR setting. Just clear all and you'll see what it's set on. Then depending on the question, you're going to set it to the number of compounding periods per year. So if you're working with semi-annual compounding, for example, you're going to set your PYR setting to 2. If it's monthly compounding, you'll set your PYR setting to 12. If it's daily, 365, etc. So first you put the correct PYR setting in, then you click on nom%, and I'll show you how to get there. Sorry, you enter if you've got your nominal rate, your quoted rate from the bank, you'll enter that, then second function nom%, and then you'll ask it for the EFF% by pressing second function EFF%. If you've got the EFF% and you want the nominal percent, you do that in reverse. So put in the one that you have and ask your calculator for the one that you don't have. So in that previous example, 2 would have been our PYR setting because it's semi-annual. 10 was our nominal rate. So we go 10, second function nom%. And when we hit second function EFF%, you'll see it'll give us the effective annual rate. Okay, so I'm going to stop sharing and show you that on the calculator. There we go. Okay, so remember when you clear your screen, orange key C, clear all, you can see that it's set on 1 PR. Now for the example that we were dealing with was semi-annual compounding. We need to set our PYR on 2, which is the number of, it's the M basically, the number of times interest is going to be compounded in the year. So you go 2, second function, PYR. And now when I press clear all, you'll see that it's 2 PYR. There we go. That's before we start. Now, in that particular instance, we had a nominal percentage rate, an annual nominal rate of 10%. So I'm going to put that in, 10, second function, nom%. Can you see that there in orange? And I want it to give me the effective annual rate. In other words, if the bank quotes me 10% and they're compounding interest twice a year, what am I effectively actually earning? So I'll go second function, EFF%, and it gives me the 10.25%. Okay, 10.25. If I had 10.25 and I wanted to know what the bank should, so in other words, I wanted to actually earn 10.25 at the end of the day, I knew that the bank compounded interest biannually or semi-annually, and I wanted to know what they should be quoting me in nominal terms, then I'd keep my PYR setting on 2, enter 10.25 as my EFF% and ask for my nominal percent. So I'm going to clear all. Still on 2 PYR. So if 10.25 was my effective rate, and I want to know the nominal rate. There, gives me the 10%. Okay, quite straightforward. I'm going to stop sharing and go back to our slides. I'm obviously going to update the Excel workshop so that you can make sense of all of the formulae in green. Right, some important tips, some of which I've already told you. You always need to make sure that the interest rate and the time or payment period match each other. So if you're looking at annual time or payment periods, you need an annual rate. If you look at monthly time or payment periods, you need a monthly rate. If you have a nominal interest rate that's been quoted to you, but it's based on monthly compounding, then you have to use monthly time periods for N. and you're going to have to adjust the interest rate appropriately. If you've got payments other than monthly, for example, if the interest rate is compounded quarterly and the repayment terms call for monthly payments. Okay, so this is getting trickier now. Your interest rate is compounded quarterly, but the repayment terms call for monthly payments. Now, don't think you can just divide the nominal rate that you've been quoted by 12 because you've got monthly payments. You can't do that because the annual rate quoted is going to be, or interest is going to be compounded quarterly at that rate. Okay, I'm going to show you just now what you do. But please don't simply divide that quoted rate that's based on quarterly compounding by 12, thinking that you're going to get a monthly rate that you can use. Let's just go through a couple of examples here or questions. What is the nominal rate if the monthly, which will be your periodic rate, remember your periodic rate is your monthly, biannual, daily, whatever the case is rate. If that's 0.5%, what's the nominal rate that the bank will quote you? Well, you can just multiply your periodic rate by M to get 6%. So if the bank quotes you 6% on an annual basis, the monthly rate will be 0.5. What is the nominal rate if the semi-annual rate is 0.5%? So here we've got a semi-annual rate of 0.5. It's twice a year. So you'd multiply that by 2 to get the nominal rate for the year. What is the monthly, which is your periodic rate here? If the nominal rate is 12% with monthly compounding, that's pretty easy. You just divide your 12 by 12, and the monthly rate is 1%. Now, this was the tricky one. What is the quarterly rate? Let me get myself a pen. What is the quarterly rate if the nominal quoted rate is 12% with monthly compounding? Okay. As I said before, you can't just divide the 12% by 4 and use a quarterly rate of 3%. You can't do that because you have to find a nominal rate first that is based on quarterly compounding. So you've got to change your nominal rate based on monthly compounding to one that's based on quarterly compounding. How do we do this? We can use our financial calculator. First, we'll take the rate itself, which is 12% with monthly compounding, and we'll convert that to an EFF, an effective rate. So I'm putting my PYR setting on 12. Then you enter 12 as your nominal percent and you ask for the effective rate. It's 12.68. Then you feed that 12.68 into your next process as your EFF percent. But now you're going to change your PYR setting to quarterly, which is 4. Enter the 12.68 as your effective rate and solve for your nominal rate with quarterly compounding. And there you'll get it, 12.12. And you can divide that by 4 to get your quarterly rate, which is 3.03, which is not 12 divided by 4, which is 3%. Because the 10% was based on monthly compounding, and you had to find a nominal rate based on quarterly compounding. So first you found the effective annual rate using monthly compounding. Then you used that to find your nominal interest rate using quarterly compounding. Okay, I'm going to use our calculator again. Okay, my setting's on 2, PYR setting. Hope you can see that. Okay, so for the first part of it, my PYR setting, because there's that 10% is monthly, sorry, the 12% is comes with monthly compounding. So I'm put 12, second function PYR. So now my setting's on 12. It's set up for monthly compounding. You can see 12 PYR. Now I have a nominal rate with monthly compounding of 12%. 12 is my non-percent. And I want to know what that translates into as an effective rate. So I ask for my EFF percent. There you see it's 12.68. Okay, now I'm going to change my PYR setting to 4 because I'm trying to find the nominal rate given quarterly compounding next. So 4, second function, PYR. So now my PYR is 4. I'm putting my 12.68 EFF that I've just calculated in. It's my effective rate. And I'm asking for the nominal rate at quarterly compounding, 12.12. Okay, which I just divide by 4 to get the quarterly periodic rate. I hope you get what you have to do when, I'm just changing that back to 1. I always do that just in case. When the nominal rate that's quoted is compounded something differently to your payments, for example, or in this case, you're asked for a quarterly rate using from that information. So you've got to first convert the nominal rate at monthly compounding into an effective annual rate, and then use that effective annual rate with quarterly compounding to solve for a nominal interest rate with quarterly compounding. Okay. Into lost my place. Okay. Here's an example of calculating the effective rate. If you can earn 1% per month on R1 invested today, what is the nominal rate? Well, you've been given a periodic rate, a monthly rate. So you just have to multiply it by 12 to get 12%. Because remember, your nominal rate is always annual, as are your effective rates. How much are you effectively earning? Well, if you invested your R1, which is your PV, at 1% for 12 months, at the end of the year, you'd have R1 13 odd cents. You'd multiply your PV by 1 plus R to the power of M, or 1 plus your nominal rate divided by M to the power of 12. It's already been done for us because they gave us 1%, the periodic rate. You could work out the rate of return by just comparing the 1.1268 that you actually get with the R1 that you originally invested. So you make a 12.68 cent return, which over your R1 that you started with is a 12.68 return. But you could use the EFF formula, or the RE, to say that 1 plus 1% or 12% divided by 12 to the power of 12 minus 1 is your 12.6668. Or as we're mostly going to do, we're going to use our financial calculators, set our PYR setting to 12, enter the nominal annual rate, 12, second function non-percent, ask for the EFF percent and get our 12.68% return. Suppose you put it in another account and you earn 3% per quarter, what would be your APR or your nominal rate or annual percentage rate? Well, it would be the periodic rate of 3% times 4, which is 12%. How much would you effectively be earning? We'll do exactly the same as we did before. This time our periodic rate's 3, our M is 4. You can see what we make and put it over our investment to get that return. You can use the future value to work it out, or you can use the formula, or you can use the financial calculator, which is far quicker. The point being that in both cases, the nominal rate was 12%. And you see that. But the effective rate was different because of the number of times interest was going to be compounding. Monthly in this case, quarterly in this case. And obviously, the more you compound, the greater M is, the greater will be your effective rate. So your effective rate increases as your compounding frequency increases. So, which would you choose? Well, they're both 12%, you say. Yes, but you've got to look and see how many times they're going to be compounded in a year. Work out their EFFs and then make your choice. You'll obviously, if you're investing, you're going to go for 1% per month or 12% compounded monthly rather than quarterly. Okay, here's another example. We've got interest rates quoted by 3 banks. Bank X is quoting you 15% compounded daily. Bank Y, 15.5% compounded quarterly. Bank Z, 16% compounded annually. So on the face of it, these 3 nominal quoted rates, annual percentage rates, it looks like Bank Z is offering you the best percent, but they're not all compounded equally or with the same frequency. So as I said, you can't compare them on the basis of their nominal rates. You have to work out each of their effective rates and then compare them on that basis. So I'm going to call up our financial calculator again. Let's deal with Bank X first. Compounding is daily, okay? So we're going to set our PYR setting to 365. 365 because there are 365 days in a year. So our PYR setting, you will see, is 365. I'm putting the 15% in as my NOM percent, and I'm asking for my EFF percent, 16.18%. This is the long way using the formula. Let's deal with Bank Y now. I'm going to clear all. I'm now compounding quarterly. So my PYR setting must be on 4. 4, second function, PYR. When I clear all, I see it's captured. 4 PYR. 15.5 is my NOM percent. What is my EFF percent? It's 16.42. And let's do Bank Z finally, compounded annually. So I don't have to worry about this one, because remember, if your nominal rate is compounded annually, then your effective annual rate will be the same. Okay. So I'm comparing 16% with 16.42 and 16.18. And if this is an investment, obviously, I'm going to go for Bank Y. If this is a loan rate that they're quoting, I'm obviously going to go for the cheapest one, which would be Bank Z. So it's interesting that Bank Z actually had the highest nominal quoted rate. So you'd think that you wouldn't borrow from that bank, but it actually turned out to have the lowest interest rate from a borrowing point of view. So you'd actually end up deciding to borrow from the bank that quoted the highest interest rate of these three. Okay. Let's go back to our slides. Jumping back. Okay, again, if you want to solve for the nominal rate, also known as your annual percentage rate, you just rearrange the effective rate equation. And that's what you get. But as I said, we're going to be using the financial calculator to convert from the one to the other. Here's an example using both the calculator and that formula. Suppose you want to earn an effective rate of 12%. You're looking at an account that compounds on a monthly basis. What rate should the bank quote you? So you have the effective rate, what you actually want to earn, but you want to know what the bank must quote you on the basis of monthly compounding. So you're going to set your PYR setting to 12 for monthly compounding, 12 second function PYR. Then you put in your 12% as your EFF percent, and you ask for your nominal percent on your calculator, and it's 11.39, which you get as well if you use the formula that I showed you on the previous page. Okay, let's move on to payments when they're not annual. So this would kick in with your annuities, etc. Suppose you want to buy a new computer system and the store will allow you to make monthly repayments. Okay. Trying very hard to get my pen here. That's the first thing you should underline. Okay. The fact that they're monthly repayments. Remember, everything hinges off the payments, the payment frequency. So they're monthly. The loan period is 2 years, so we're going to have to convert that into months by multiplying by 12. The interest rate is 16.9%. Thank goodness with monthly compounding, so we can work with that. And the question is, what will your monthly payments be? Okay. So as I've said to you before, you can either leave your PYR setting on 1, and then you'll have to do the work for your calculator by dividing your annual rate of 16.9 by 12 and using that monthly rate. Either method that you use, you've got to convert your years into months, 24, to match your payment frequency. So if your PYR setting's on 1, it's 2 times 12 because 24 is your N, 16.9 divided by 12 is your IYR. Your PV is minus 3,500 because that's what it's going to cost you. And your payment will be 172.88, your monthly payment when you solve for that. Or you make your calculator divide the interest rate by 12 by entering 12 as your second your PYR setting. Then you put the annual rate, the 16.9 in as your IYR, 24 is your N, negative 3,500 as your PV, and solve for your payment. Same answer. Your preference, which way around you want to do it. Either have your PYR setting on 1, the first way, and then you've got to divide your rate by 12 and enter that as your IYR, or make your PYR setting 12 and put in your annual rate and your calculator will divide it. And remember this PYR setting, as I've said quite often before, it only only affects your interest rate, your IRR. Still have to make your N in terms of months in this case. It doesn't multiply that for you. All right. I'm going to quickly do that with the calculator for you. Where to put it? Okay. So either, I'm just going to check what is my POR sitting on. It's on 4. So I'm either going to put it back to 1 and then just enter 24 as my N. 16.9 divided by 12 equals that is my IRR. 3,500 is my negative is my PV. What's my payment? Or I'm going to change my POR setting to 12. 12, second function POR. Again, put 24 in as my N, but I can put 16.9, the annual rate, the nominal rate in as my IRR because the calculator will divide it for me. 3,500 is my PV and the payment is 172.88. Okay. Here's a future value with monthly compounding example. And we've got 2 examples coming up. This couple are considering an investment which involves payments of 400 each month. Okay, month, years. Interest rate is 12% per annum compounded monthly, so that's good. How much will the investment be worth at the end of 5 years? Okay, so important to note that the payments are monthly. Now we've got to convert these 5 years into months. So 5 times 12 is 60. The interest rate offered is 12% per annum, compounded monthly, which is great. And what will the investment be worth at the end of 5 years? So we're looking for a future value. Okay, so again, either leave your POR sitting on 1 and make it, then you have to do the work in terms of entering your interest rate as a monthly rate. So your 60N goes in, 12 divided by 12 equals 1 goes in as IRR. Your payments are minus 400 and you're solving for FE. Or put your POR setting on 12, enter your 60N, just enter 12 as your interest rate because it will divide it for you. Minus 400 is your PMT and you get the same FV. Okay. Here's a more complicated example. Company deposits 10 million per quarter. Okay, for 5 years. So everything hinges off these deposits, which have quarters. So everything's got to be in terms of quarters. So we're going to have to multiply 5 by 4 to get the number of quarters. Interest, unfortunately, is 6% per annum, but compounded on a monthly basis. We want to know what the future value of their deposits will be at the end of year 5. So this is like that previous example I showed you, where your interest is compounded and a different frequency to what your payments are going to be made. So first we've got to find an interest rate that is going to correspond with quarters, a quarterly interest rate. And we've got an annual interest rate compounded on a monthly basis. Okay, N will be 20 regardless. So let's try and get an effective annual rate for monthly compounding. So 6 is our quoted rate, 6%, quoted nominal rate. So we enter that 6 section function non-percent. And because we've set our PYR setting to 12, the effective rate will actually be 6.16%. Now we set the PYR to 4 to account for quarterly compounding. We enter that newly calculated effective rate and ask for the nominal rate with quarterly compounding, and we get 6.0301. Now we can work with this rate because it's a nominal rate, but it's based on, it's 6% per annum, compounded monthly, but converted to a quarterly compounded rate. So we're going to keep our PYR setting on 4. We're going to enter 20 as our N, this nominal rate of 6.0301 as our percent. The calculator is going to divide it by 4 because of the setting here. Minus 10 million is our payment, our deposits, our quarterly deposits, and we hit FV. Okay. Or you put your PYR setting on 1 and you divide your 6.0301% nominal rate, annual rate by 4 to get 1.5075 and use that as your IYR. Your choice, same answer. Okay. So follow that process when they're not corresponding. The frequency of your payments is not corresponding with the compounding frequency of the interest rate. I said that you don't really need to worry about continuous compounding, but here we've got daily compounding. You need 150,000 in 3 years' time for a new car. You can deposit money into an account that pays a nominal rate of 5.5% based on daily compounding. How much would you need to deposit? Okay, so it's a lump sum deposit, and you've got a nominal rate of 5.5, and it's going to be compounded daily. So that daily rate would be 5.5% divided by 365. And your number of days in a 3-year period is 3 times 365, which is 1095. So again, you either leave your PYR setting on 1, enter 1095 as your N, put 5.5 divided by 365 equals your interest rate as your IYR, your 150,000 is your FV because you need that amount in 3 years' time or 1,095 days' time, and then you hit PV. Okay. Or you put your PYR setting on daily, which is 365 setting. Then you can enter your 5.5. Enter your annual rate here instead of dividing it. Your calculator will do it for you because your setting's on 365. Everything else is the same. 1095 is your N, 150,000 is your FV, hit PV, and you get the same answer. Okay. Continuous compounding is where it's just 24/7, 365 days of the year, it's compounding your interest. It doesn't really happen much in the real world, and I'm not going to go into the maths behind this formula. You can work it out, though, if you want to. You can work out the future value if you are working with continuous compounding, but I really don't want you to sweat too much about this unless you're interested. Okay. And here we've got a retirement fund example, which I'm throwing in before we move on to amortization. So here we've got an investor who wants to retire in 25 years' time. She's due for a pension from her employer, but she wants to supplement this or add to it by contributing to a retirement fund of her own. Through this retirement fund, she wants to receive a monthly pension of $6,000 a month for 12 years after she retires. And remember, she's retiring in 25 years' time. So for the 12 years after that, she wants to receive $6,000 per month. Okay. So we're going to have to convert all these years into months at some point. In addition, she wants to receive a lump sum payment of 1/3 of the accumulated sum from the retirement fund on retirement. So in 25 years' time, she wants to have enough in this retirement fund so that she can take out 1/3 and enough will be left there, which is the 2/3 left over, excuse me, such that she can draw down $6,000 a month for another 12 years after that. Okay, and that's actually how most RAs work. When they mature, which you set your retirement date as the maturation date, they generally offer you 1/3 thereof tax-free, and then the rest is in the form of an annuity for you for the next however many years. Forget I said tax-free because it's not always the case. So, but there are tax implications of doing it that way. In addition, the fund is earning a return of 12% per annum, interest compounded monthly. Okay, so the payments are monthly. Unfortunately, they're compounding periods monthly as well. And that return is expecting to remain in place for the next 37 years, which is actually the time period for this whole scenario, because retire in 25 years' time, get $6,000 a month for 12 years after retirement. It's a 37-year time span. Question, determine the monthly contribution that the investor must make to the retirement annuity fund over the next 25 years so as to achieve her goals. Now, this is a classic example of when you need a timeline. Okay, so she's sitting here now in time period 0. She's going to start by making monthly contributions towards her retirement fund. Obviously, I can't fit them all in, but she's going to do that for 25 years or 25 times 12 months. I'm just going to put 25 here, but we're actually dealing in months. That's 25 years' time. And then she's going to start drawing down 6,000, or she wants to be able to draw down 6,000. Sorry, that's 6K every month for the remaining, for the next 12 years, which takes us up to year 37. Okay. So the question is, how much does she need to have? Well, the question is asking, what do these monthly payments have to be such that she has enough here upon retirement to take out 1/3 in cash, and the other 2/3 that she leaves in the fund must be able to generate 6,000 every month for her for the next 12 years. Okay, so we're going to tackle this in a step-by-step basis. It's often better when you're working with PV questions to work from right to left. So let's deal with this stream of 6,000, this annuity stream of 6,000 receipts that she wants to earn. There are 12 times 12, 144 of them, because she's going to be drawing it down every month for 12 years. So 12 times 12 is 144. So we can work the present value of that annuity as at this time period here. And I think you'll agree that that will represent the 2/3 that's going to be left behind. Okay, so then we can work out the whole amount that needs to be in place here by the time she retires. And then we use that whole amount as a future value of an annuity and solve for the payment for however many, for 25 times 12 payments. That'll be the N. And we've got the FV of our annuity, and we solve for the payments. All using an annual rate of 12%, but compounded monthly. So we use 1% per month. Okay, so that's the nuts and bolts of it. So step one, working from right to left, we're going to calculate the present value as at retirement date that has to generate an annuity of 6,000 per month for 12 years. So because the interest is compounded monthly, I'm putting my PYR setting on 12. I'm entering the 6,000 payment. It doesn't have to be a negative because it's going to be, how much you have to invest? No, it is, because you're going to draw it out of it's going to be an outflow. She's going to draw it out of this fund. She's going to be drawing that out of the fund every month for 12 years. So that's 144 is our N. 12 is our IYR. The computer will divide the 12 by 12. And the PV is 456,823. Okay, so that is going to take care, that portion of the accumulated fund is going to take care of the 6,000 that she wants to receive every month for 12 years after retirement. Now that is going to have to represent 2/3 of what she'll need upon retirement. She's going to take out 1/3 and leave this amount there, which is the other 2/3, so that that can generate the 6,000s every month for 12 years for her. So if 456,823 is 2/3 of the amount she needs, what is 3/3, or what is all of it? Sorry. So the full amount that she requires, we'll just divide 456,823 by 2/3, which is the same as multiplying by 3/2. And 685,200 is going to have to be sitting in that fund by retirement. 1/3 of which she'll withdraw as a lump sum. The other 2/3, which is 456,823, will stay there and be able to generate this future income for her. So if she needs to have accumulated 685,200 by the end of her, by the time she retires, how much does she have to put aside every month for those 25 years such that that will be the future value? Okay. So keep your PYR setting on 12 because the interest is still being compounded monthly. Put the 685,200 in as your FV. Your N will be 25 years times 12 because there'll be 300 contributions that she'll make every month for 25 years. 12 is the IYR. The computer will divide it by 12 for us. Then you hit payment and you get the amount that she needs to contribute every month starting in a month's time from where she is now for 300 months, such that it will have accumulated to 685,200 by the time she retires, so that she can withdraw 1/3 in cash and leave the rest, which is 456,823 there, to be able to generate the 6,000 per month that she's going to need for the next 144 months. Okay. So a timeline certainly helps. And then you use all the principles that I've taught you to solve the problem. I've made a note on inflation and returns here because I think it's appropriate. It's going to come up again later on in your finance studies. But as you know, inflation reduces what you can do with your money over time. So for countries like ours with a positive inflation rate, prices go up all the time, and that erodes the value of your money because it affects your purchasing power. So when a bank offers you an investment rate of 4.8% per annum, and inflation's running at 3% at the same time, then you're not really going to make 4.8% on your money, are you? For example, if you invest 1,000 Rand at 4.8%, by the end of the year, you'll have 1048. How did I get that? I multiply 1,000 by 1 plus 0.048. And by the end of the year, I'll have 1048. However, just to buy what I could have purchased with 1,000 now in a year's time is going to cost me 1,030. How did I get that figure? Well, I inflated my 1,000 by the 3% inflation rate. So I grew it by 3% and multiplied it by 1.03. So I might have 1,048 by year end, but just to buy what I could have the year before, that takes up 1030 of my 1048. So it's just to illustrate that we really need to consider inflation in any investment decisions, especially when you're making pension decisions. And we use the Fisher effect formula to solve for real rates of return if you have a nominal return and you know what the inflation rate is. So in this particular example, if we use the formula 1 plus the real return is equal to 1 plus the nominal return divided by 1 plus the inflation rate, normally that's referred to as H. That's little r. Oops, I didn't mean to get that line. And that's big R. Rearranging, we can solve for real return, and it's all of this minus 1. So in this particular example, the real return is the 1.048, which is what we, it's 1 plus the nominal rate, which is 1.048, divided by 1 plus the inflation rate, minus 1. So in real terms, when we're investing at 4.8% in nominal terms, and inflation's running at 3.3%, we're actually only really going to make a real return of 1.75%. Which is quite sad, really. But more on this in later chapters. Okay, this is a very long recording, and I want you to go and take a break, pause your recording, and then come back again later. I've been carrying on for a long time, but I don't have much left, so I do want to continue it all in the same session. So the last thing I want to teach you about today is loan amortization. Now, the process of amortizing a loan is when you pay it off by making regular principal or capital reductions. So it can happen in two different ways, this amortization of a loan. You either pay equal installments of capital over the duration of the loan period, and you pay interest on the reducing capital balance. So as you owe less, your interest drops. So only the principal is fixed, the capital repayment's fixed, the interest changes. Or you pay it back in fixed payments, which include capital and interest. And this is the most common type of method of where loans are amortized. Most of your consumer loans work in this way, your car loans, your student loans, your home loans, etc. And I'm going to illustrate both of them now. So, firstly, we're looking at an example where you have a fixed principal capital payment. So, suppose you take out a 5,000 loan that requires 5 equal annual principal repayments. So you're going to pay this 5,000 off in 5 equal principal payments of 1,000 each. Can you see that? Now, interest is going to be at 9% compounded annually. If you're asked to draw up an amortization schedule, this is how you do it manually. So right now you owe 5,000, or in the beginning. you're going to pay 1,000 off in principal, and you're going to also have to pay 9% of interest, which amounts to 450, 9% of 1,000. Sorry, 9% of 5,000 is your interest for the year. And the principal of 1,000 plus your interest means your loan repayment will be 1,450. But at the end of the year, in terms of the principal, you'll still owe 4,000 because it'll be the 5,000 loan minus the principal that you paid will be 4,000. And that's the same every year. You're reducing that principal by 1,000 every year until it's zero. And in the meantime, you're paying interest on the reducing capital balance, the amount that you still owe. So at beginning of year 2, for example, you still owe 4,000. So 4,000 times 9% will be your interest plus your 1,000 Rand principal repayment means you pay 1,360 and so on. So by the end of the 5th year, you've paid off the principal, you've paid a total of 1,350 in interest, and your total loan repayments of capital, principal plus interest is 6,350. Okay, so that's when you're paying back a loan where you've got fixed principal payments. That's what you've negotiated. The other way is when you pay back the loan in equal annual installments, total payments, which would include principal and interest. Okay, so same amount of the loan, repayable in the same time period, but by virtue of 5 equal annual installments that include both principal and interest, not just principal like the example before, and your interest will be at 9%. The loan amortization schedule will look like this. But first, we've got to calculate that equal annual installment. We know how to do that. It's the payment when it comes to an annuity. So we enter 5,000 as the PV of the loan, 5 is the duration of the loan, 9 is the IYR, and the payment, which includes both principal and interest, will be 1,285.46. So that's how you populate your loan payment column. And you work through it year by year. So you owe 5,000 in the beginning. At 9% thereof is what you pay in interest. So the principal that you must have paid, if the interest portion of this 1,285.46 is 450, then that minus the 450 must equal the principal that you've paid. And therefore, at the end of year 1, you will owe 5,000 minus 835.46. And that'll become what you owe at the beginning of the next year, and so on. The second year, that's your total payment. 9% of this beginning principal is your interest. Therefore, the difference must be your principal that you've paid or your capital, and you take that off your opening principal to get your closing principal, and so on. And in that way, by the end, you've paid off the loan. You've paid back your principal in total of 5,000. The interest that you've paid in total is 1,427, and your total payments on the loan are 6,427.31. Now, if you compare the two, this proves to be the more expensive way of paying back a loan. The interest paid is more with this method, and the total loan repayments that you make is more. It's not always going to be the case, but in this particular example, it's because this way the loan is paid off a lot slower early on. So, for example, these 3 years here, you're paying off the loan itself at less than 1,000 Rand a year, whereas previous way you were paying off 1,000 Rand from the beginning, and that meant that your interest would be lower. Okay. So that is how you would work out or set out an amortization schedule. You can, however, use your financial calculator either to populate a table like that, or if you just want to find out, after so many years, how much will I still owe on this loan, etc. So what you do is you enter the details and you solve for payment first, like we had to do for the second method anyway. So we arrive at our 1285.46. We leave that in our calculator. Then you press second amort, and I'll show you where you find that. And that's going to give you details about the first year. The first time you press equals, after that, will give you the principal paid in the first year. Press equals again, it'll give you the first year's interest that you pay. Press equals again, and it'll give you the closing balance of that amount at the end of year one. And then you press second amort again, and you can repeat the same for the second year, the third year, the fourth year, etc. Each time you press second amort, you're looking at a different year, and by pressing the equal button, you get the principal, the interest, and the closing balance, respectively, for that particular year. Okay, so it's very useful. I'm going to show you now on the financial calculator. There we go. So I'm clearing all, and I'm making sure that my POR setting is still on 1, which it wasn't. Now it is. Okay, so first we've got to find that payment. So we go 5,000 was our PV. That's the amount of the loan, the PV of the loan. 5 is the duration of the loan. 9 is the interest rate. And we need the payment. Okay, so it's 1285.46. Now, I want to amortize this loan and divide this payment up into principal and interest payment each year, as well as see what I owe at the end of each year. So I'm going to press second function, amort. Can you see amort at the top here? The same as my FV key. That's going to amortize this payment for me, or this loan. So I go second function, amort. And you'll see now it's going to show me the information that I need about year one. Okay. So every time I press equals, I'm going to get a different piece of information about year one. I press it once, and that is the principal repayment that I'm going to make, 835 odd rand. Equals again gives me the interest that I'm going to pay for that year of 450 rand. Equals a last term gives me what I will be owing at the end of year one, which is 4164. Okay. I'll do the same for any other year. So I'm going to go second function amort again. This is for second year. And each time I press equals, I get the information about the second year. Okay. And I can do that for all the years. So I could use my calculator to populate a table if that was what was required. Or if I just needed to know what I would be owing on my car loan after 3 years, I could use the calculator to work that out as well very easily by looking at the details under the third year. Okay, so financial calculators really do make time value of money and loan and investment calculations very easy for us. Okay, so that was our very long lecture. My apologies. The last slide is just all about using Excel to draw up an amortization schedule. It's quite complicated, but Excel is very user-friendly, and I will go through it in the workshop that I'll post shortly. So thank you for bearing with me, and we'll see you on the flip side. Take care. Enjoy your long weekend. Bye.